Hi, you guys. Today we're going to learn about the Earth's history and how it's recorded in the rocks. One day, one of you asked me why I like geology, and I didn't have an answer that day, but I've thought about it, and I know. I like geology because there are beautiful rocks out there, and they make beautiful landscapes, but they also tell a story. The whole history of our Earth is recorded in rocks, and if you know how to read those rocks and what story they're telling, you can figure out what happened in each place that you visit. That's why I love geology. The geologic history of Earth can be read from rocks if you know what to look for. So in this presentation, you will see examples of many types of clues that are stored in rocks. We're going to start by reviewing how rocks are formed. Now remember, igneous, metamorphic, and sedimentary rocks are all formed differently. So what are the differences? Well, sedimentary rocks form from layers of sediment that collect in horizontal layers. Over time, with pressure and chemical cementing, rocks form. Remember, this most often happens underwater, where sediment is washed down by the water and laden in a layer, and then the next layer is washed down, and the next layer. And over time, the pressure of that water compacts all of those sediments, and eventually they're cemented together. Now, behind this young person and dog, you can see layers of sediment. I would guess, just looking at it, that those aren't cemented together yet, that's probably the edge of a wash, or more likely the edge of a river, the bank, where it's been cut away. But down in the bottom left-hand corner, where you can see the people in the raft on the river, that's definitely cemented. That's rock, and it's cliff-forming sandstone that over thousands or perhaps millions of years has been worn away by the actions of that river. Sometimes the layers are exposed by erosion, like these canyon walls in Dinosaur National Park. Dinosaur National Park is by Jensen, Utah, which is just a little past Vernal, Utah. It's a beautiful, wonderful place to go and visit. These layers are found near Denver, Colorado, and they show how horizontal layers can be altered by uplift. In this case, the Rocky Mountains rose and changed these layers. Can you tell which layer is oldest? Well, the layer that is on the far left is the oldest. This doesn't make sense. Should layers get laid down vertically like this? Probably not. These got uplifted and pushed into this position. Sometimes layers of sedimentary rock are twisted by earthquake faults. This is another picture from Dinosaur National Monument, and it's called Split Mountain. And you can see this beautiful curve in these rocks, and that's because there was a fault here that split the mountain in half, and over time and all of the movement caused by this fault, these sedimentary layers were twisted. Here, this is Price Canyon, one of the railroad cuts in Price Canyon. It's a little bit of a fuzzy picture, so watch this white layer right here. Because of a fault, which is right here, this layer no longer lines up. You get to the fault, and the layer's up here. There are some faults in Price Canyon where you can count as many as 7 different faults in one cut. The reason is because this is the edge of 2 different geologic zones. Somewhere through Price Canyon, the boundary of the Colorado Plateau and the Great Basin exists. It's not like a defined boundary where you go, all right, I'm crossing this line. I'm moving from the Colorado Plateau into the Great Basin. It's a few miles wide, and so it's really chopped up, and there's a lot of fault lines in that area. This is a picture of Beck Spur, which is north of Salt Lake City. It doesn't look like this anymore. Most of that mountain's gone. This picture, you can look at this truck and see just how old it is. This picture was taken a long time ago, and when I was a kid, this is what it looked like. The cliff is the Wasatch Fault, and it was not made by people. So this cliff right here, it's not cut away by people. Up here, this one was because it's a gravel pit. Down here, people didn't cut this one away. When the Wasatch Fault slips, the mountains rise, and the valley where most of Salt Lake is falls. Okay, we're going to get a little closer here. You can see these layers are they're kind of diagonal. There's been some uplift over here on this side. These have been pushed up. Now these layers are pretty much horizontal, so these layers are newer. These diagonal layers, when they were laid down originally, they were horizontal. They would have been going across like this. But something happened, probably uplift, the movement of the Earth's crust, and they got pushed up. Well, they got eroded away. You can tell because right here, there's a nice flat horizontal line. Something eroded them away. Probably water, maybe wind. They were eroded away. And then sediments were brought in and laid down in layers on top of them horizontally. Look, you can see even closer some scratch marks and probably some contact metamorphism. So right under this thin layer is probably sandstone. But this top layer has been metamorphosized, probably into quartzite. And it's happened because of all the heat and pressure that happened as the fault moved, as these two big pieces of crust moved past each other. So there's the scratches that formed as the rocks slipped by each other. Now, sedimentary rocks have clues to past climates and ecosystems. These rocks, which are part of the Navajo sandstone, which we have a lot of right here in Carbon and Emery County, especially in Emery County. These rocks were ancient sand dunes, and the layers with layers that formed at different times and at different angles depending on which way the wind blew. When I get back, When I get back, I will be able to explain better to you what cross bedding is and why we can find it all over southern Utah and how you can use these layers that are on an angle to figure out which way the wind was blowing. It's a little hard without drawing a picture and being here to tell you in person. If you go bike riding on the Slip Rock Trail in Moab, you've ridden on ancient sand dunes. So you've ridden across the top of the Navajo sandstone layer. What kind of climate do sand dunes suggest? Was this wet? Was this dry? Was this an ocean? Was this a desert? You can see the trail in the picture that's marked with white dots. I personally have never been there, but I hear it's pretty fun. Well, this was a desert or dry climate. In fact, it was the largest desert that the Earth ever knew, or at least as far as we have found evidence that's saved in the rocks. See, this is one of those stories that the rocks can tell us. This desert was massive. It was much bigger than the Sahara Desert, and it was huge, and it existed for a very long time. In some places, these cliffs, these ancient sand dunes, are 50 feet tall. Now, some of us have seen ripple marks in the rocks, and in fact, I saw some ripple marks. See this hammer? It shows you how big they are. I saw some ripple marks over spring break. Well, because of the law of uniformitarianism, which, if you know, is my favorite word, the law of uniformitarianism says that the natural processes that are happening today, they have always happened. So whatever's forming ripple marks today is the same process that formed ripple marks millions of years ago. Well, in the top picture, you can see examples of ripple marks in the sand next to a river. So on the edge, there's ripple marks sometimes. And apparently Sam the dog really likes ripple marks. And down here in the bottom, there's fossilized ripple marks. And scientists assume that because they find these ripple marks on the edges of rivers now, that this rock that's fossilized must have been the edge of a river millions of years ago, because that's where ripple marks are formed today. Now, if I found ripple marks in just north of the town of Emery, which is where I found them, wouldn't you say that the town of Emery at one point Would it had a river, or maybe even a beach? Maybe even a big river? I don't know, but I find lots of ripple marks around the town of Emery. What formed these marks in an environment long ago? What do those trails through the rock look like? Oh, whoops, I gave you a hint. Well, those are worms burrowing through soft sand or mud. We know because the law of uniformitarianism tells us that the same processes that exist today existed millions of years ago. And today we find marks like that in soft sand or mud, and we find worms that have made those marks. In fact, you could go over to the class pond and you could find tiny little versions of those worm burrows in the glass. I mean, in the mud inside of our pond. Now, what might conditions like these form? It looks like there's maybe a flood. You can see some things have been washed down in this river. It's not the greatest picture. But this is the edge of a river in Dinosaur National Monument. What do you think this would have, what kind of rock would this form? Well, did you say that maybe dinosaur footprints or other preserved remains of plants or animals? Because fossils are direct clues to the past. And a fossil, in order for a fossil to form, the organism has to be buried quickly, or its trace, its track, or its tail mark, or its skin imprint, or the imprint of the leaf. It has to be buried pretty quickly. Otherwise, it gets weathered and eroded away. So since fossils are direct clues to the past, this one was part of a series of footprints near Denver, Colorado. And the circle around it is where someone has attempted to cut it out of the rock and steal it. That seems pretty selfish, but, we've learned, now we know better than to do that. We have learned that it's better to leave it where it is and let other people go and enjoy it in its natural environment, and that we can learn so much more from it, leaving it in its natural environment. So let's think about this for a second. Did this dinosaur walk across a rock and leave a footprint? Did it walk across some gravel and leave this footprint? Could it have walked across dry sand and left a footprint as good as that? Or do you think it was probably a little muddy? Not too muddy, but just a little muddy, and that when it walked across it, it left that footprint. Think about where you leave footprints when you walk across it. Mud is usually the best place to leave a footprint, as long as it's not too muddy. Utah has lots of dinosaur fossils. These fossils that you can see are inside of a building are skeletons that are displayed at Dinosaur National Monument. Now, it says it's displayed. It sounds like people put them there, right? Here you see a neck and you can see a skull. Here you can see a foot and a leg. Well, these weren't displayed by humans. They are displayed by nature. Scientists have dug some of these out of this rock wall, but many of them have been left there so that we can learn more about it and so that people can go there and see this beautiful formation. The person has been placed there for size comparison. That's about the right size for a real person. When you go to Dinosaur National Monument, you can see almost fully articulated skeletons. It's pretty much awesome. And the wall that these are in, this layer, has been uplifted, so it's almost vertical. It's like looking at the wall in our classroom and having it be covered in dinosaurs, only huge. It's very big. Can you find ribs? Can you find vertebrae? Can you find some carbon remains from a tree trunk? That means, can you see some black stuff, like coal, left over from a tree trunk? Can you see a shoulder blade? Maybe a thigh bone? Okay, there's the tree outline. There's the rib bone. There's some vertebrae, or part of the backbone. Over there's a thigh bone. Right there's a shoulder blade. All right, now igneous rocks sometimes flow upwards into cracks in other rocks. Oh, hold on, wait a minute. Can igneous rocks flow upwards? No, magma can. So sometimes magma flows upwards into cracks in other rocks, and then it cools and forms igneous rocks. Okay, the igneous rock in this picture is light colored, and it has intruded or made its way into darker rock. It's in a Y shape. It's right here. Here's one side. Here's the other, and it comes down right here. What happened first? Well, this darker rock was deposited first, and then somehow it cracked. Whether there was an earthquake or there was some other kind of movement, this rock had a weak spot. And there was magma underneath the crust that was under pressure, and it was trying to find its way up. And it found this weak spot, this crack, and it slowly made its way up. Maybe it quickly made its way up, but it made its way up. And then over time, it cooled down. It probably took a long time to cool down, thousands of years. So now you have an intrusive igneous rock right here, and we call it an intrusion, sorry. Can you see igneous rock in these rocks? Now remember that sedimentary rocks are in layers. So first look for the layers. They're not exactly horizontal. They're kind of on the diagonal here. So when they were originally laid down, they were straight across horizontal. So we've had some uplift that lifted them up, this side up. Then somehow there was a crack. And we had some igneous, some magma come and fill in that crack. It probably pushed and made the crack bigger. And then it slowly cooled over time. So first, horizontal layers were deposited. Then they were compacted and cemented. Then there was movement which caused a crack, and the magma came in and filled in the crack, and then it slowly cooled over time, and then you have igneous rock. Well, sometimes as igneous rock cools, valuable minerals like gold and silver collect around the edges, and they're said to form veins. So when you find igneous rock like this, that's where you want to look for gold. There's that igneous rock. And unconformity, so let's think about what unconformity means. If you conform, then you're just like everybody else, right? And unconformity wouldn't be like everything else. So an unconformity occurs when erosion removes the top surface of land and the surface is then reburied. Now, we've looked at this picture before. We talked about it. Here's the unconformity right here. In geology, you look for unconformities when the layers go in different directions. So here, these layers were originally laid down horizontally. We know that because that happens today. Then some uplift happened. Then the top surface got eroded away, and it was eroded away pretty horizontally, so it was probably by water. And then the surface was reburied over time with many layers of sediment. So the question is, can you find the unconformity in this picture? Well, you can now because I just showed you. But it's right there. To interpret Earth history, a diagram called a stratigraph is sometimes used. It uses symbols to stand for rock types and can be decoded if you know your Earth history. So the first thing you have to remember is that sedimentary layers are always laid down horizontally originally. It's called original horizontality. Okay, take a look at this stratigraph and see if you can see the order that events happened. Okay, so here's the key that you're going to need to use. This one with kind of bigger dots is conglomerate. These smaller, pretty uniformly laid out dots are sandstone. Little blocks are limestone. And these dashes are shell. So, I'm going to take that back. What happened first? Well, look at the bottom layer. It's going to be the oldest layer. This layer was laid down first. And look over here. Oh, it's limestone. And we remember, limestone was born, not made. So this must have been underwater. This was a marine environment, maybe the bottom of the ocean. less likely it was the bottom of a freshwater lake. We'll call it ocean because most of the time, that's where limestone forms. We know because that's where it's forming today. Okay, so this limestone formed. It must have been an ocean. Then it changes. All of a sudden, it's sandstone. Well, at this line right here, this period of time, something happened to the environment and it changed. Maybe it was different for a long time and we don't know it. Maybe there were a million years of the ocean dried up and for a million years nothing was getting, no sediment was getting put down. Maybe the change happened faster than that. Maybe it was the ocean and then some reason either the water levels dropped or maybe the ocean floor rose and it became the beach. And now we have a layer of sandstone. So that's what happened second. The next thing that happened, and I know that because look, limestone, same, sandstone, same. Now these two line up. So that must have been the third thing, this layer of shale. Now remember the hill that our elementary sits on, actually the ground that our high school and junior high sit on is shale. This usually is deposited in really low energy water, like a deep ocean, a deep sea. So it must have been that either the ocean levels rose again or the land sunk again, which sometimes happens. And now this was really low energy water environment again. We had lots of shell laid down. Okay, then we have a fourth event. Look right here, they don't line up. Well, we have this line. This is called a fault. The fourth thing that happened was there was a crack, a fault, and either the left side sunk down or the right side went up. With just this stratigraph, it's really hard to know which happened. And honestly, I'm not very good at figuring out which one happened. There are geologists who specialize in that, and they're very good at it. I struggle with figuring out which side went up and which side went down. So, just to check, the limestone formed first, then the sandstone, then the shell, then an earthquake faulted the rocks. The earthquake fault occurred last because the rocks had to all be there before they could be offset. Okay, now time for a harder one. Does it look scary? It's really not. Okay, there are 10 steps, including the events that happen to the rocks. First, can you see the unconformity? Oh, we're going to go back. Okay, unconformity, remember, the top layer got worn away, and then new layers got deposited on top. Okay, first, we're going to say that this conglomerate got laid down first. Sometimes you're going to want to say, I just can't tell. It's diagonal and it looks weird. Well, think about it. Is it likely that it got turned clear upside down and that this would be on the bottom? Probably not. There was probably some uplift here. Something was pushing up over here to make the land rise. So this is probably the bottom. So we're going to say, number one, conglomerate was laid down. Second, this sandstone. Third, this layer of limestone. Fourth, this layer of sandstone. Fifth, this layer of shell. Now, something happened. There was some uplift. Oh, we got to have the uplift is 6. Then erosion to wear all that away was 7. Number 8 was this limestone. 9 is this sandstone. 10 is this shell. And see how it's not a flat surface? It's all different. It looks like, hills and some valleys. That's going to be the last thing that happened was erosion. They say there's 10 events, and I say there's 11. So let's see where we're a little off. Okay, here are the events. Ready? Conglomerate, sandstone, limestone, sandstone, shell, erosion, limestone, sandstone, shell, erosion. Oh, I added the uplift there. They didn't add the uplift, so that's where the change was. There's your unconformity. Okay, now you get these weird ones. Remember the pictures where we saw the igneous rock that filled in the cracks? Okay, igneous rocks intrude into other rocks. Think about if you're with a group of friends and somebody comes and intrudes, they kind of butt in, right? Well, igneous rocks intrude into other rocks. Because they're hot, they affect the rocks that are near them. So where you see these lines, what kind of rock would get really hot, but it didn't melt? And it changed. Its form changed. Oh, that's right, metamorphic rocks. Okay, so look at this stratigraph and see if you can list the steps. These dark lines show contact metamorphism. So only the rocks in those regions are metamorphic. Okay, what happened first? Did you say that this layer of limestone got laid down? What happened second? Did you say this layer of sandstone? What happened third? There was something that caused this crack, and then the magma intruded, and it cooled. So this layer of igneous rock is going to be third. And what happened fourth? That's the contact metamorphism. Kind of happened almost at the same time as this. Probably took a little longer for these rocks to change, though, than it took for this magma to come in, and then this lava to fill in on the top. Okay, so what type of rocks are heated but not melted is metamorphic. It goes sandstone, limestone, igneous, the volcano. Okay, we're back to that same old picture. How many times do we have to see this? Well, it's a good picture, that's why we keep seeing it. Can you label the geologic events in this picture? What happened first? The shell was laid down. What happened second? Think about the unconformity. Oh, erosion. What happened third? Conglomerate came next. Then fourth, we got some shell. They left out that there was some uplift, some sort of movement to make this more diagonal, but that's all right. Oh, and last, remember the top's not flat. We have some erosion up there. Landscapes can tell us about Earth. Can you walk out of your school and see landscapes? You can go into Mr. Wild's room, Miss Peterson's room, and look out the windows, and you can see a beautiful landscape. What history does that tell you? Well, as you look out that window, you don't realize it, but you can see a coal bed, which is an ancient swamp. On top of that coal bed, you see layers that indicate that it was a beautiful beach. And you see layers that have conglomerate rock with dinosaur bones in them that says dinosaurs once walked this earth. If you look out the windows in this classroom, you can see shell that says, hey, and you can even see fossils out there, great big clams that say, hey, this was once a deep ocean. All kinds of history are in the rocks. And if you know how to read the rocks, they tell a great story.